Okay, so here we have the first derivative test, and this is going to be a test that will help us tell whether or not a critical number is actually a local max or a local min. So we will start with a critical number of a function f, and then we can use the first derivative test to characterize that critical number as a local max, a local min, or neither, because sometimes we have critical numbers that are not actually local extrema. But so there are three possibilities. If f prime changes from positive to negative, then we can conclude, at the point C, then f has a local max at C. Okay, so notice if a function goes from positive, or if the derivative goes from positive to negative, that means that f goes from increasing to decreasing. And so if we draw like a little sketch of what that would look like, notice that we would have a local max. So that's how I remember these conditions. So for a local min, it goes the other way. So if the derivative changes from negative to positive at the point C, then f has a local min at C, right? And then the third case is if f does not change sign, if f prime does not change sign, or let me actually write this out in complete sentences. So if f prime does not change sign, then f does not have a local extreme at C, right? Okay, and so I forgot to do the corresponding sketch for a min. So if f prime changes from negative to positive, that means that the function changed from decreasing to increasing, right? So it could look something like this. Notice that even though the derivative does not exist at that critical point or critical number, the function does still change from decreasing to increasing, and we have a local min here. Here we had a max, right? If we had a local extreme, but the derivative did not actually change sign, one possibility of what this might look like is that we have a horizontal tangent, so the function flattens out. We have a horizontal tangent, so that would give us a critical number there, but the function just keeps increasing afterwards, so we don't get a local min or a local max in that case. Okay, now when we actually go about using this, there are a few steps we have to do before we actually apply the test, right? And so it's going to be very similar to the example that we did in the first video. Right. So first of all, we will start by finding the derivative and the critical numbers. So you will need to find, maybe I'll say it this way. So find the critical numbers of f. Okay, critical numbers of f you'll need to find f prime to do this, right? So really the first step is to find the derivative. And then you'll find the critical numbers by finding all points where the derivative is either 0 or undefined, and then and make sure that those points are actually in the domain of the original function. And then the next step is to make a sign chart like we did in the previous example. So this is going to be a sign chart for f prime so that we know all of the places where it is positive and negative. And then we apply the first derivative test to characterize the critical points as local maxes or mins, or neither, because it could be the case that we get that it's neither. Okay, so let's take a look. Here I have this function that we used in our in-class work a few classes back, and I want to look at it in terms of the first derivative test and sort of analyze it in that way. So first off, let's just make a note of all of the local extrema. So we're not going to look at the endpoints in this case. We're just looking at the what's going on in the open interval, -2 to 2. And so we see that we get a minimum right here. So I'll go ahead and record that. So we have a local min at, this looks like approximately -1.2, something like that. And then we have a local max right here, right? So we'll record that one as well. Local max at, this looks like it's approximately 1.2. And then we have a local min here. And that looks like it's approximately halfway in between 1.5 and 2, so 1.75. Okay, and so what I'm going to do is beneath the this graph, I'm going to draw a number line, and then I'm going to mark each of the places where we have a horizontal tangent or the derivative does not exist. So there are 4 of them, and then I'm going to label each interval where the function is increasing and decreasing, and see if we can use the first derivative test to get the same answers as what we wrote down here, right? So it's basically like using the first derivative test, but we happen to already know the answer. Okay, so here we have, I'm going to go ahead and erase these, so we're not thinking about these right now. We're looking at for places where there's a horizontal tangent or the derivative does not exist. And so we get a horizontal tangent here. So that will correspond to a 0. So I'll go ahead and put a 0 here to indicate that the derivative is 0 there. So this is, we're charting f prime. At 0, at x equals 0, we get another 0 here. And then here we have another horizontal tangent, right? And then lastly, we have this point, so that is going to make the derivative undefined. So I'll just write UND for undefined at that point. Okay, and then like we were doing in the previous example, we can just fill in each of these intervals with the sign of f prime. And so instead of using the formula, which we don't have for this function, we're just going to use the graph to determine this. So looking at the first interval, so it does end right there, so I'll go ahead and put endpoints on this graph. So on this first piece, starting from the left, the function is decreasing, so I'll put a negative sign over that interval. After that, the function is going up, so it's increasing until we get to this point where we have the horizontal tangent. Now, after that point, the function keeps increasing, so we'll put a plus here. And in fact, I want these to stand out a bit more, so I'm going to change the color. Okay, so we are up to this point. We have a horizontal tangent at that 1.2, and afterwards the function starts decreasing, so we'll get a minus, or we'll put a minus sign on our number line, and then after this pointy part, the function starts to increase again, right? Okay, now we can look at this and use the first derivative test to try to figure out where there are local maxes and mins, right? So just focusing on the first critical point right here, the function does change from negative to positive. So let me go ahead and label these with the x values as well, so that it's a little bit easier to just read it off from here. So this was negative 1.2, 0, 1.2, and 1.75. Right. Okay, so at, we'll say x equals negative 1.2, f prime changes from negative, I'm just going to go ahead and use a plus and minus just to save space, to positive. And if we look up at the first derivative test, so this would be the second condition, f prime changes from negative to positive, then we have a local min. So we get a local min at x equals negative 1.2. I guess that part is kind of redundant because we wrote that at the beginning of the sentence. Local min there. Now going to the next point, so that will be at x equals 0. F prime does not change. So that means that we don't get a local extreme. At next we have x equals 1.2. F prime changes from, let's see, we're here at 1.2, so it goes from positive to negative, and so that's going to correspond to a local max. And then finally, let's squeeze this in here. At the last point was 1.75. F prime changes from negative to positive, so I'm just looking at this part of my chart, or this is my number line. It changes, F prime changes from negative to positive, so we get a local, so if it's going from negative to positive, that's going to, so it's going from decreasing to increasing. So I guess I like to think of it this way. So negative to positive means decreasing to increasing, and that means you'll have a local min at that point. Okay. So we did get a local min at negative 1.2 and another one at 1.75. And then we got a local max at 1.2. So of course, we already knew the answer, but this does confirm to us that this is how we can find local extrema. Okay, so we are going to do an algebraic example in the next video.